So to start off, we're going over the distance sensors or the infrared sensors that will give us the distance reading to the walls around the maze. This is kind of, we kind of went over this last time, but we're going to have 5 of those sensors, and the infrared transmitter or the infrared LED will transmit a light, and it will hit the walls or objects around it, reflect that by light, and then we'll receive it on our infrared receiver or photo transistor. And depending on how much light hits this infrared receiver or photo transistor, it will open the gate of the transistor or essentially turn the switch on or off less. So it's kind of like a dimmer switch, you can imagine. As more light hits it, it'll be brighter, and as less light hits it, it'll become dimmer. And again, this is the circuit here. We have the LED on the right-hand side with a resistor hooked up to it with a transistor acting as a switch. So the transistor will be open until we send a signal through the infrared LED GPIO pin that we have defined in our CULB IDE. So, for example, if we send a high signal, or if we apply like 3.3 volts right here, it'll go through the current limiting resistor, go to the gate, turning on this switch, which will then allow current to flow through the LED, through the resistor, and to ground, thus turning on the LED. On the opposite side here, we have the phototransistor, which will take the light emitted from the LED and bounced off the object and turn this gate on more or less. So, for example, we have 3.3 volts right here, and let's say that the transistor is turned on enough to be like 100 kiloohms. In that case, we have a voltage division of around 100 kiloohms here and 300 kiloohms here, which would give us like a 25% voltage drop right here, because if in total with 100 kiloohms with 330, it's roughly 400 kiloohms. Thus, 1/4 of the voltage will drop here, and then 3/4 of the voltage will drop here. But if more light hits it and this becomes, let's say, 5 kiloohms, then 90% of the voltage drop will be across here, and we can read that with the STM32. And so here is an example of the LED being turned off and on below. So this blue line right here is the LED getting pulsed, turned off and on, and then above it is the voltage across the phototransistor. So this is an example with a wall in front of the phototransistor, and thus we are actually receiving a voltage feedback from our phototransistor. However, you'll notice our input is pretty much a perfect square wave as we send a signal to our LED. However, our output for the phototransistor takes a second before it reaches its peak. This is because it actually takes a second for the infrared LED to turn on. So you can imagine like a light bulb, one of the old incandescent light bulbs, kind of take a second to warm up and heat up. LEDs kind of do the same thing, except much, much faster. This first peak that you see happening right here happens in 250 microseconds. So between the start of the LED turning on and the peak of the reading of the phototransistor, it takes roughly 250 microseconds. So in our code, we want to be able to turn on the LED, take a reading, but not immediately. We want to wait to get to the peak of our reading. So we're going to wait 250 microseconds, take a reading from our phototransistor, wait another 250 microseconds, turn the LED off, wait another 250 microseconds, and then take a second reading from the phototransistor right here, and then it repeats. Then it turns the LED on. The reason that we want to take a reading of the peak phototransistor and the valley of the phototransistor is because naturally there's ambient infrared light in the room, and so we want to be able to take this peak value, or take the peak value and subtract it by the valley value. And that way we can kind of get an unbiased result of how far that object is, no matter how much ambient infrared is in the room. So we have a state machine that we have here to describe the process that we want our microcontroller to do. So first of all, we have our different states. This is state 1, this is state 2, this is state 3, and this is state 4. Starting off, we're going to see if the state has changed, and in the very first one, we can assume it has changed, and then it jumps into this. State 1, turn the LED on. And then it jumps all the way through this because all those other states are not happening at that time. So then it goes back to here. And then it loops this. So you can see the little arrow here. It constantly loops this until 250 microseconds has passed. Once 250 microseconds has passed, we want to go to the next state because we want to read that value right there. So once 250 microseconds has passed, an interrupt in the microcontroller will happen, which will add one value to our state. So we're starting at state 1, 250 microseconds pass, plus 1. Now we're at 2. Thus, the state has changed from the previous state. Previously it was 1, now it's 2. So we can go through here and go to state 2. We want to read the photo transistor. And then it's going to go out here, go ahead and loop this for 250 microseconds until the next state is changed. And so then it'll go through here, go to state 3, boom, loop here until 250 microseconds has passed, and then boom, go to state 4, take the final reading, and then subtract the photo transistor reading from when the LED is on versus off. So I'm going to skip that for now. But to code this into Cube IDE, we need to do a couple of things. First of all, from the oscilloscope, we see it takes around 250 microseconds before the phototransistor reading is at its peak value, and another 250 microseconds before it reaches the valley. So we have the 4 states we described earlier at 250 microsecond intervals. And so that's just kind of going over what I just said right there. But to do this, we need some way to add 1 to the states every 250 microseconds. And the way to do this is the same way that we decided our PWM signals for the motors. If you remember, we went and found exactly how to get a 24 kilohertz frequency from our motor driver. So we're creating a PWM signal that is at 24 megahertz or 24 kilohertz. However, in this case, instead of focus on frequency, we want to focus on the period. So period and frequency are just inversely related. So for example, the period of 24 kilohertz is just simply 1 divided by 24,000. In this case, we're already starting with period, which actually makes our calculations a lot easier. So yeah, so I kind of right there. So we know that our timer is going at 84 megahertz. So that's how fast it's counting up. It's going like 0, 1, 2, 3, 4, 5, 6, 7, 8, at 84 megahertz, which is very, very quick. And our timer period is just our exact frequency divided by 1. And we know our desired period is 250 microseconds. Thus, to find our new counter value, which if you remember in our last lecture, we talked about counters, and once they hit a certain limit, they will overflow. So for example, if we have a counter that is 3 bits long, it will be able to count up to 8. So 2 to the power of 3 is 8. So it'll be able to count to 0, 1, 2, 3, 4, 5, 6, 7, and then jump back 0, 1, 2, 3, 4, 5, 6, 7. I'm not going all the way to 8 because I'm counting 0. It's like 0, 1, 2, 3, 4, 5, 6, 7. That's 8. Our counter value is how much our counter will count up to get our desired period of 250 microseconds. So we can just simply divide our desired period by our timer period. And if you do these calculations, I kind of forgot to put it here, but you'll end up with, I believe, 2,100 or 21,000. I think it's 21,000. We'll go over that in a second. But so now we have a new timer counter value of 21,000, meaning that it will count at a speed of 84 megahertz. So it'll be like 1, 2, 3, 4, 5, at 84 megahertz, and then once it gets to 21,000, it'll stop and then restart at 0, right? However, every single time a timer interrupt occurs every single time our system overflows. So in my example with only 3 bits, every single time it goes from 7 back to 0, an interrupt will occur. And an interrupt is simply something that jumps out of the code where it currently is and then runs that little bit of code and then jumps back to where it was. So you can imagine it, it's like, if you're running a race and then you need water, you got to stop for a second, drink water, and then go back to it. That interrupt is what's happening right there. The code is just running. Boom. It has counted to 21,000. Jump out of the code where you're currently at, run a tiny little bit of code, and then jump back in it. So we can use this interrupt that occurs every 250 microseconds to change our state. So just to go back to the state machine right here, that is how our state is changing. Our timer interrupt is interrupting every 250 microseconds to add 1 to the state, which will change the state from 1 to 2. And it'll check if the previous state, for example, if the previous state was 2, and then it's just looping here, and then boom, the timer interrupt happens. It jumps out of the code, adds 1 to the state, and then now, like for example right here, now the state is 4, but previously it was 3. It goes here and goes, oh, okay, the state has changed. Go through here, runs the 4th state, and then makes the previous state value equal to 4, and then jumps back here and does that over and over again. So hopefully you kind of understand that a little bit better when we actually start to code it here in a second. So let's open up Cube ID.
Cube ID, where do I download it?
It's all good.
Yeah.
Yeah. I'll send you
And I know I'm going pretty fast here, but I'm trying to give us some more time so we can actually start kind of programming and things like that.
Yeah. Yeah. We'll go through and
So, I already have it there. Let me jump into this one. I don't know exactly what's in here. I just want to make sure that. Well, one. Where is it? Let me just get set up here in a second. That should be there.
It's okay. So mine's a little bit different. Yours is going to be within Visual Studio Code.
I don't know, it's not there.
Straight. I have it as a separate action here, and then I bring it into
Okay.
Studio, but it's the same.
I'm just going to use the same thing and just cut my code out. So, whoops. All right. So you don't have to remove your previous project. I can't remember what we did last time. It was the analog reading, right? So we did this bit, correct? Oh, it's the Discovery F401. It's going to be in the boards.
Yeah.
I got
What
it.
is
Discovery F401.
I'm not sure. Disk?
There you go. Good. So, what was that? Oh, so going to the board selection? Yeah. Since we're using the Discovery,
You have to you just search it in there, but
one, so you can go into STM32,
F4.
F4, and it's the discovery one, F401. I believe that's it, actually.
The first one?
Yeah, F401C
All I
discovery.
did was within
Yeah, you can start a new project. I probably should start a new project. You know what, matter of fact, let me do that. That way I can. All right. So we're using the 411 for our final project, but this is just the specific board we're using to dev right now. But eventually we will use the 411. But if we're gonna be doing the project using this specific board right now, we can use the F401. So I'm just gonna go ahead and create a new project and go over that really quickly.
Feel free. It's also touchscreen if you wanted to use touchscreen, but you can just take it. I'm not worried about it.
And just out of curiosity, have any of you had any experience or heard of state machines before? Any? Yeah. So exactly, yeah. So I think they go over a little bit of that in 301, but that's just that same process there.
STM32 F401
Disco.
Yep.
Yeah. Yeah, it's obsolete. That's fine.
That's what it looks like. I did it.
Click here.
You get it.
Lecture
Yeah,
3.
mainly I don't have it in Visual Studio, but I did it with.
So again, we're gonna be doing it in C,
We have a whole different method.
and you could just do all default modes right there.
In there, you have to set like what you're coding in and different things, but mine's different. So you can also move up to the front, and then you'll see on the big screen, yes, it's projected.
Yeah, I know. I'm kind of covering it.
Yeah, I would recommend you. You can look at the screen. There's also a chair there.
Yeah.
So.
All right. So I hopefully you guys are kind of close to this part right here. So again, this is just our board right here. And all these green ones are the ones that are already defined by the discovery board. So, you know, for example, there's LEDs on this board. So they already have all those defined for us. We don't need to worry about that. Essentially, the first thing that we need to do is find a timer to use. Because remember, we're using the timer to be able to actually count up and down. I'm going to use timer 4. The yellow little symbol right there just lets you know that some of the channels might be disabled. So for example, channel 1 and 4, I cannot use those. Those are currently being used by other pins. However, I'm welcome to use channel 2 or 3. But, yeah. So I'm going to use channel 4. And the first thing that we want to do is select our clock source. Again, this is going to be an internal interrupt, and so we're going to be using our internal clock. So just like when we were doing the PWM generation, we're going to have this thing come up at the bottom, the parameter settings. I believe I didn't do the calculations back there, but if you guys don't mind checking my work, let's go ahead and do the calculations. So
divided by
so you guys can pull out. It's simple.
is it e to the 6 or is it e to the 9? Megahertz is
6.
Yeah.
Oh, well, you have to divide that first. So we're dividing because it's gonna be period, not frequency. So we're gonna have our desired period, which is 250 microseconds, divided by our timer period, which is our timer period is 1 divided by 84 megahertz. Okay. And I don't know if you guys have seen in your class either, like working with frequency that T represents the period, and the period is always 1 divided the frequency. And the period is just how often it happens. Mm-hmm. So what number did you guys get?
21K.
21,000. And remember, since we're starting at 0 and not 1, I'm just going to subtract 1 from that. And so our counter period is now going to be 20,999. So we're going to go ahead and set our counter period to be 20,999. You got that downloaded fast.
No, that's my computer.
Okay.
But also, I wonder ahead of time about the Visual Studio because
Cool.
I'm a weird
Yeah.
CS guy, apparently.
All right, the next thing that we want to do is go into the NVIC settings and set this to be a global interrupt. So this will be an interrupt that just happens globally. That way we can actually interact with it. Okay.
This is where?
If you look right above right there. Yep. So again, the parameter settings right here, we simply just changed the counter period. We don't have any prescaler, and the NVIC is enabled right here. And just to go back for a second, I'm going to go back to this same problem right here. And now let's imagine instead of doing a desired period of 250 microseconds, let's do it to be 1 second. So do that same math right now. So instead of choosing a desired period of 250 microseconds, you could just do 1 second. So let's say you want an interrupt to happen every 1 second. You could just make an LED blink every 1 second with an interrupt like that. And then what value do you guys get?
$84K?
84K?
Yeah. Because doesn't it just end up being you pop that up to the side? Okay, yeah.
So our value, right. You guys are getting 84K. If you notice, before I messed with this,
Or would it be 84 meg, just the same?
Yeah, it would be, I guess. Before I mess with this, I guess I'll choose this one. If you notice, our counter period cannot go up to 84,000. The max amount that we can count to is 65,535 because that's 2 to the power of 16 since it's a 16-bit counter. So to get around that, you can do you can see right there between 0 and 65,535. In a case like that, where you need to have a speed slower than the slowest possible speed, then you would need to do something like have a prescaler. This is just something that you're going to multiply to be able to get a kind of larger, it essentially slows the clock down. So in that case, you can get you can get to your desired point. So I'm just going to turn that back off again. But I just wanted to show you that we're not having to deal with prescalers right now, but I want you to know that if you have something that you want to interrupt, something slower than your maximum counter period, you can do things to get around that. So we have our counter period right now to be 20,999, which means that every 250 microseconds now, we will have an interrupt happen. But nothing else is happening. Right now, the interrupt just happens, but we haven't put any code in it. In addition to that, we don't have the code to read the analog to digital converter. So I'm just going to go ahead and add this one right here to be the analog to digital converter so we can read the value coming out of our photo transistor. Since it's not a digital signal, we're reading change in voltage, which is an analog system. So I'm going to just choose that to be an analog to digital converter. And you really don't need to do much else for that, you know. You don't really need to touch any of this stuff. I choose this one at the bottom right here, PA1. In addition to that, we need a pin that can toggle our infrared LED to be able to turn it off and on, right? Since we want to turn the LED on, take a reading, turn the LED off and take a reading. So we're going to use pin PA8 right here. And I'm just kind of picking these because those are the pins I already put them in. But again, any of these pins can have a variety of different peripherals that we can set. So instead, if we wanted to, we can use PA8 as our analog and PA, that's PD. Oops. PA8 is right there. And we can use the other one to be the digital output. But in this case, I'm just choosing this because those are the pins they already have set here. So it's going to be our GPIO output. And that way we can turn our LED off and on with this pin. The GPIO stands for General Purpose Input Output. So we can send a 3.3 volt signal out of this, or we can send a 0 volt, like a signal to ground out of this. Or if we want it to be an input, it can read a digital input. So it can read if a value is 0 or 3.3 volts. And we can also have it be an analog if we choose it to be an analog. But in this case, we're having it be an output such that we can turn our LED off and on. So now that we have our kind of 2 pins that we need to read our analog to digital converter and turn our LED off and on, or to read our phototransistor, I'm going to go ahead and do Control S to save it. And you'll recognize when you do that, it's going to ask you to generate code. Raul, you might need help for this part. So every time you save it, it's going to generate code with those new peripherals that we just chose already written into our program. So I'm just going to hit yes.
There you go. Okay, and then just generate code should be fine. And you gotta go into VS and open it. For this side, it's a lot easier because then you just generate it, goes straight into the thing. But for mine, I have to transfer. But it works the same.
All right. So once the code is generated, again, you'll realize there's a bunch of stuff that is a lot to look at and it's really scary. But I hope that last time you kind of realized that we're not actually writing that much code. Everything that's going to happen is going to be in our while one loop that will loop indefinitely. And the peripherals that we set outside, if you remember, we had a analog to digital converter that we set on channel 1. So it auto-generated it here for a type def for that. In addition to that, we also have our timer that we set up, which was timer 4, if you remember. So this is just kind of setting up stuff for the timer and the analog and digital converter. But we don't have to write any of this because thankfully Cube IDE and HAL kind of auto-generates it. Roll.
Yes. Oh, yes.
All right. So all right, so let's go back to our main loop. So we have wait a second, I guess, and I'm kind of just gonna.
You said most of the code we write is in a while one loop?
Yes. So this is like 90% of our code that we will write. This will just indefinitely loop. We're gonna have a couple of things that it will initialize in the beginning, but everything will essentially after that will just be looping this forever. If you used Arduino before, they have like a main loop that just kind of loops indefinitely. This is the same exact process. So this will just be just constantly looping no matter what. You have a question?
No, I found it. While one loop, right?
Oh, yes. And then in addition to that, if you weren't here for the previous lectures, we talked about the user guards, which you can see it says user code begin while, user code end while. We need to write our code in between these guards. If we write it outside of it, next time we generate code, it will delete it.
User code, right? User code. I'm gonna write space.
You can actually give.
I don't think it's going to delete it on yours because you're on Visual Studios.
So it's here.
Yeah, you're fine there.
It still does the same. It's just kind of it looks weird when it has to do.
Oh, there it is. User code begin while.
Yeah, it's still.
This
same.
is the loop.
Okay.
Yeah, so write it in between those guards.
Here and here.
No, user code begin while and user code end while. So write it in between those two right here. you can see the user code begin while is right above the while one, and the user code end while is kind of right above that little USB host process thing.
Yep.
So we want to write it inside of our while loop. So it's going to be starting right here. Now to jump away from this, we're going to have a couple different variables that we need to declare. So we need a variable we need 3 variables for the photo transistor. If you remember, we're going to be reading the photo transistor when the LED is on. We're going to be reading the variable of the photo transistor when it's off. And then we also want a variable with the difference of the two. So subtracting the off from the on. So at the top right here, we're going to have the user code begin 0. So this is the private user code. This is where we can define a lot of our variables. So to define variables in Cube IDE, you have to be kind of specific on what the variable is. So if you remember in your 186 class, I don't know if they talked about different types of variables, how you can have an unsigned number or an unsigned integer or a signed integer. So in 201, 301, they talk about that. The sign is just like, a positive and negative. In this case, all of our values are going to be positive. So I'm just going to do U, signifying unsigned, and then it's going to be an int. And then I want it to be a 16-bit variable. And then just underscore T. And then I'm just going to write this as PT, photo transistor, LED on. And then I'm going to make that equal to 0 in the beginning. And don't forget your semicolons. After every end of line on C, you need a semicolon to signify the end of that line. So we have the first one, the unsigned int 16 for the photo transistor on. And then I'm going to make another one.
You have to repeat that same variable. Repeat it one more time, or 2 more times.
All right. In addition to the photo transistor variables, we also have a new variable that we're adding, which is going to be the state. So if you remember, we were talking about before the state. So I'm just adding one more here, just called state, and this will define if our LED is going to be turning on, if we're going to be reading the photo transistor, if we're going to be turning the LED off, or if we're going to be reading the photo transistor again. So this goes back to our state diagram, and I'm just calling a variable state to be defined as the variable that will know what state we're at. In addition to that, we also need to know what the previous state was because we want to check if our state has changed, right? So I'm going to do on16 underscore T, and I'm just going to call it, I'll use uppercase, previous state is equal, and I'm equaling it to 1 right here, and it'll kind of make sense why I'm doing that in a little bit. But we're going to have our state, and then we also need to store our previous state. In addition to that, we have a little bit of information regarding our analog to digital converter that I cannot remember the exact syntax for, so I'm going to reference this back here. So, okay, yes. So I'm going to just kind of move that into here so you guys can copy this. Now, I'm actually going to go ahead and make, sorry about this, 1 second. I'm going to make my screen a little bit bigger so you guys can see it a little bit easier. Did that change much? Okay, cool. Hopefully this is a little bit easier to see. Cool. So we're going to have a status type def. Essentially, this is just defining if the analog to digital converter is running okay or not. And so this is just a value to just keep track of the analog to digital converter, making sure that it's running okay.
What are we using for the timer channel?
It's channel 1, timer for channel 1, but we'll initialize it in a second here down here.
What are you selecting for the parameter? Like, what are you selecting?
Oh, yeah. So it's going to be internal clock. And then in addition to that, in the priv settings, you want it to be a global variable.
Got it. Thank you.
Mm-hmm.
My computer does not like this.
We like one. I mean, this should be fine for now. Unidentifier is undefined. So maybe get rid of the T. Let me see if that works.
You might have to build first as well.
Yeah, maybe. Oh, whoops. You might have to build first. Maybe. Yeah, I don't. His is a little bit different than mine.
Yeah.
So you're gonna have to deal with the consequences of his.
It still works fine, even if you were to build it.
So essentially, that's just kind of keeping track of our analog to digital converter. If something goes wrong with it for any reason, this will be kind of they say HAL okay or error. So essentially, if an error happens, this will be an error value, or otherwise HAL okay just means that everything is running good. So this just status type def is just kind of what the analog, if the analog to digital converter is okay. So now that we kind of have our variables defined, so we know that we're going to be having 3 different values for our photo transistor, and then we're also going to want to keep track of our state and our previous state. So the next thing we have is our initializations for our timers and such. So we need to actually start our timer. Otherwise, if we don't initialize or start our timer won't ever start. And if our timer doesn't ever start, then it's never going to count up, and we're going to be really confused as to what's happening, and then eventually be like, oh, I didn't initialize my timer. That's what all the CE guys, I've been in here so many times where they've been debugging for 30 minutes, an hour, and eventually they go, oh my gosh, I didn't initialize my timer. And then boom, they figure out what their problem is. We're going to go ahead and initialize our timers. What was that? Outside of the while loop, yes. So this is in user code begin 2. This is where we can kind of initialize things. This will run once in the beginning and then really won't run again after that.
It's not indented the same as the...
Yes, that's where we're going to initialize all of our timers and stuff. I am still getting used to this, so I'm going to try to do this off memory. I believe it's HAL, and then whoops. Whoops. What I just did?
No, I actually did the same thing.
What the hell just happened? Oh, Lord. Give me a second.
Yeah, I took
What did I just do?
CS 100 or whatever the class was instead of 186. So I did the exact same thing. Yeah. I took 186.
I accidentally just created a second screen of it somehow. I know what I did. Not really sure how to.
I never learned but I ended up learning the project.
All right, whatever. I'm gonna leave it for now. So HAL, and then this is timer. Was it? Okay, yeah, I gotta go back. I forgot what it was. Okay. So, I mean, I can copy this whole thing, but this is just kind of a little bit of an extra guard. So essentially the main thing we need is this. So this will actually start our timer. So it's HAL time base start IT, that. Essentially what this if statement is doing right here is just saying, okay, is the timer starting? Is it started? And it'll check if it started. So HAL okay. If it is not okay, so the little exclamation mark means not. So if HAL is not okay, then it'll send an error handle. It's not super necessary, but it's nice to have a little bit of an extra protection in your code.
Just that thing is there, so I can't see it.
Yeah, I'm like, it's all right. I don't need it.
It's okay. You don't need
It was in the example.
No, the thing inside of the brackets. I can't see the first
it's
thing.
at the ampersand.
Oh, yeah. So yeah, HAL Tim base start interrupt timer, and then it's going to be the and sign or ampers, and then H for handle, and then it's going to be timer 4.
I'm so sorry. Yeah, it is the and symbol, but it's also ampersand, which is like term.
Yeah, I didn't know that.
Yeah. I only know that because of CS people.
Yeah, of course.
Exactly.
All right, so now our timer will start once it hits this line in here. Okay.
Well, if it doesn't always turn green, it will return a different color.
Yeah.
Yeah, I heard. I saw that.
It's not like what it's wrong about.
Unless
It might give you, yeah, it's kind of like sometimes it doesn't change colors until I hit the build right here, the little hammer. But that being said, if something doesn't color up, I'll be like, okay, did I write this right?
mine
So-
shouts at me for like anything you type
I'm
before
probably
you
not
type
gonna get
build.
very
Yeah.
It hates it, so I don't know.
this semester, but it's like
Yeah, and don't forget the semicolon at the end.
it's just like
All right.
Cameron.
So
Cameron's been a deal.
the first thing that we want to do is check if the state is greater than 4. So we only want our state to be between 0 and 0 and 3. So we want to check if our state is greater than 3 or not, because in our state machine we don't have anything planned for after 4. Or in this case, 0, 1, 2, 3. So I'm just gonna write a little if statement in the beginning here. It just says if state is greater than 3, then state is equal to 0. So if the state is greater than 3, make it back to 0, because
not having an engineering class, it's challenging math. It's math that actually makes me think for a minute.
How's this going, Adam?
good. Some of
Good
them.
to hear.
Yeah, I'm forgetting a lot of the syntax, but I have a reference right here.
That's C for you. Yeah.
Yeah. All right, so I'm kind of going to jump out of here for a second, and this is where we're going to find the interrupt. So obviously, right now, the interrupt is happening every 250 microseconds when our code is running, but nothing is happening inside that interrupt. So it'll jump out, realize there's no code to run, and then just jump back in. So we need to actually add the code to be able to do that. And if you're going to be very kind of specific, I have a link that I posted in here, which gives you a really good guide to where you would find it. So they go into exactly where it is because it's not in the main function. It's actually kind of in another.
Where are these slides posted?
The slides will be posted after the lecture. I'm just using this as a reference right now to look at, but you guys will be able to access these after the lecture.
These intro lectures, which are like really useful to the proof your key lady. It looks like there's a whole lot of code in it, but it's actually really not that code. And the cube kind of does a lot of
It'll just go back to zero.
It'll
in terms of coding.
if there's essentially it won't ever count up. It'll just go out to the interrupt and says, what do I do here? There's no information here, and just go back. So even though the interrupt is happening every 250 microseconds, it's not changing the state. So we need to add one to the state. And again, You can open this specific file to find the interrupt handler, and this is the name for it. I'm just gonna go into there, and I believe it is right here. So it's oops. So it's somewhere in this kind of mess where it's outside of our main function. It's in the IT, which I believe stands for interrupts, but it is the void. Where is it? Second. Oh, here it is. Is it?
Yeah.
So how Tim IQR?
Source, which is already open. No worries.
Is it the
STM?
STM32 F underscore IT? Okay. So
No, you're no one is like caught up right now. We're all generally he's verifying that he's doing the right thing by checking his reference, and we're all waiting. That's fine.
okay.
Is it just gonna be how to IRQ handler and then it's gonna be like the and HM4?
Sort of. I can't. Okay, so I can't remember exactly where it's in here. I believe it's underneath one of these. I'm just gonna kind of skip this and just go to the actual value that we're gonna be putting in. So if you scroll all the way down to the bottom of the code, you'll find a user code begin for. Oftentimes, this is where you'll put your functions. So user code begin 0 in the beginning. That's where you define your variables. The other one is where you get to kind of initialize your things. You have your user main code loop, and user code begin for is kind of where you put your functions and things like that. So the function title that it's going to be running through once it. All right. So I'm just going to retype this for you so it's a little bit easier to follow, but it's just going to be void how Tim period elapsed callback. And essentially, this is the function that will happen when the period has elapsed or it's gone through the entirety of the counter. So once the entirety of the counter has overflowed, it will jump into this function. And we're going to define the function and what happens in that function when it happens. A lot of functions there, but essentially, we're just going to say Tim.
It's going to feed it.
Type def.
H2.
So, yes. So now, once the once the counter has has completely overflowed, it will run to this function. Now we need to define what happens once it runs into this function. And if you remember, we had the states before, and we wanted the state to increase by 1 every 250 microseconds. So every 250 microseconds, this function will be called, and we want to just add 1. I'm going to delete this just because it's double, but
Yeah, duplicate it. See if it'll fit.
yeah.
Yeah. I gotta show you the meme after. I'm sorry about that.
Right.
C. I love C.
So now every 250 microseconds, our system will add 1 to this state. And if you want, so where's it at? It's always a struggle. So right now, all our code is doing is every 250 microseconds, it jumps to that function below, adds 1 to the state, comes back to the while loop and loops, and then just checks if the state is greater than 3. If it's greater than 3, create it to 0. Right now, nothing else is happening. However, we want to also create the if statement to check if the state has changed. So if you go back to kind of our state diagram here, you can kind of see that we need to check if the state has changed. Right now, all we're doing is just changing the state and keeping it in between 1, 2, 3, and 4, but we need to write some function that checks if the state has
Otherwise,
changed.
it's going to run every time the loop runs, and that's not good.
Yes. So I'm going to come back here. I'm going to do an if state is not equal to previous state, then we're going to run that sequence of events that we had planned back there.
Did you define previous states yet?
Yep.
Where is it?
On line 76.
Maybe remember the line.
Someone asked me earlier
Did
what the
you
line was.
update previous state in your interrupt yet?
Oh, yes.
Oh,
Oh, no, the previous state updates when it goes into the case switch.
oh okay.
Yeah, because otherwise,
that makes
yeah.
sense.
Can you hold on that line for a second?
Yep.
There you go. You're good. And then that's how they do it in the beginning.
Yeah, it's all there then.
Mhm.
Yeah, that's the tricky bit because if you don't do that, then the function doesn't work as intended.
My God, you
Or if you're not running it.
It is.
Yes.
That curly bracket just means that after this if statement, everything in between this curly bracket will happen.
Yes.
So the curly brackets in C just means that after like a logical operation, whatever is in that will happen. Or if a function is happening, this is going to be everything inside the function between those curly brackets.
I wanna do it for this problem. It's gonna
Yeah,
be
go for
fun
it.
about this.
Yeah, do it. Yeah, have fun.
So
I think that's their stuff.
It's like 430 studying. I think that's
I
probably
mean,
alright.
if you make them write it out again, it's good for their study.
Yeah, that's what I was gonna say. Like,
So just erase it.
Probably
Go for it. Go for it.
it's probably alright. I mean, it's a general purpose board.
I mean, they're taking a break. When they get
Yeah.
back, they'll have to be fresh out. Anyway.
all right, so now we need to write the logic for the next part of our state diagram. So we need 4 states. It goes, okay, if the state is 1, turn the LED on. If the state is 2, read the phototransistor. If the state is 3, turn off the LED. If the state is 4, read a phototransistor and subtract the phototransistor reading when the LED is off. Now, I used ifs right there because everyone at least is familiar with if statements. However, we're going to do something that's a little bit more efficient. We're going to be using switch case statements. Just kind of, I don't know, just show of hands if you guys have ever worked with switch case statements before. Okay.
Technically be covered in 186. but
yeah.
depends heavily
If
which
you take
professor you get it.
186,
And that, yeah, if you took 186.
I didn't.
Yeah.
take it.
That's no big deal. Switch cases are essentially just something that it checks a variable and then will go to that case if that variable is equal to the case. So, for example, I'm going to write switch state, and then we're going to have another set of curly brackets to indicate now we're inside of this state.
Inside the switch, yeah.
Inside of the switch, sorry.
Does there have to be space between these two? Does it matter?
No, the space doesn't matter. I just personally do it. So we're going to have case 0.
Isn't it case 0?
Is it case? Yeah, there we go. Yeah, that's right. And then now we're going to be running through this set of case. And before I put the information in there, I'm just going to go ahead and just do the other cases. And then in the event that for whatever reason the case is not 0, 1, 2, or 3, it shouldn't ever not be 0, 1, 2, or 3, but we have something called a default.
Good practice.
Yes. So If for whatever reason the case is not 0, 1, 2, or 3, it's going to go to this, which is the default. The reason that we might use a switch case instead of a bunch of if statements is because for if statements, first of all, it's a little bit messier to look at. Just a lot of if else, if else, if else, if else. Second of all, with if statements like that, it'll go through the if statement and let's say, for example, these are if statements and it runs through and the first if statement is correct. The program will still check all the other ones. It'll say, okay, is it this? Is it this? Is it this? Is it this? And then it'll continue your code. Versus switch case statements, it says, okay, is it, instead of running through that, it just says, okay, we're case 2, jump to case 2, execute it, and then jump out.
Well, you need to have the break for the jump.
Yes, yeah, we'll add it there in a second. But that way it doesn't actually have to go and check every single if statement.
Saves a lot of seconds.
Exactly. So the first thing that we want to do is turn the LED on. So we're going to do HAL GPIO what is it? Yeah, I have it here. I did. Yeah.
It needs to set the pin high.
Yeah.
You have to call the function to set the pin high. Because it's HAL, it's a ridiculously long name.
It is.
Isn't it just
I could.
HAL GPIO toggle?
No,
Toggle. Oh, right pin. That's right.
Yeah, you want to avoid toggle
So-
because we specifically want to turn it on in case it's some weird state.
And I forgot another useful part of Cube IDE and HAL is, let's say I'm like, I kind of don't remember the exact name because it's really long. As you're typing, you can hit Control and then space, and then it's going to give you all these different things that are following it. So already it notices I wrote HAL GPIO _, and in this case, we're doing the right pin. So I can just, again, as I'm typing, I'm going to move away for a second and come back. I'm going to do Control space, and then all of a sudden, look at all these different options that I can choose from. And as I go back,
Just use HAL.
then there's all these different ones that I can choose from. But if you do Control space, I don't think you have that. Do you have that option? Yeah,
It's
no.
automatically like it's adjusted.
Oh, okay, it's automatically in that one. Okay, cool.
Mine's different. That's why.
But that way you can find it, and we know it's a GPIO, so GPIO, and then I'm like, oh, okay, we're trying to write the pin, and writing the pin just means we can write it high or write it low, or essentially turn the pin on or turn the pin off. Give the pin 3.3 volts or give the pin 0 volts and turn it to ground, essentially. So I'm going to double click that just to make it a little bit easier. And it's going to autofill all that stuff that we need. Almost. The last thing that we need to do is actually define what pin that we're writing high or low. Again, if we go back to see which pin we chose, in this case, we chose pin A8. So the P stands for port. So it's port A, pin 8. And again, there's different ports. So there's ports A, B, C, D, and each one roughly counts up to like 15, I believe. So there's port A, 1, 2, 3, 4, 5, 6, 7, all the way up to 15. Then it goes to port B, 1, 2, 3, 4, 5, 6, 7, all the way kind of roughly up to 15.
Yeah, because each one I think is like one register.
Yes. So this is going to be port A. So the X right there is where we're going to define what port it is. So it's port A. The next thing we want to do is define the pin, and it's pin 8, and it's going to be GPIO _ pin 8.
Yeah, I think the underscore is not showing very well.
Yeah, it's not showing because there's a little like, whoops.
Yeah, there's some formatting issues that happens.
Underscore 8. So that was correct.
Yeah, it is.
I don't trust
And now we need to set the pin state. So we're going to want to do the pins. We want to set the pin. So
Set in all caps.
SET in all capitals.
set.
Yeah.
And then don't forget your semicolon. So we're using the GPIO output to set this pin high. So we're going to be sending a 3.3 volt signal out of port A, pin 8. So that we can turn the LED on.
It's just as a point of amusement. I'm just letting you know. Set is set or reset, which is the other one does. It just writes a 0 1 to it. It's just easier to read set or reset.
Yeah. All right. So now, kind of Leo mentioned this earlier. Once we do our intended thing, we need to do a break. I forgot. 1 second. So before we can do that, I'm going to write previous state is equal to state. So now, once it jumps back out, the previous state is going to be equal to the state it once was.
So it won't run again until the state is changed.
Correct. So this is where it's going to check that. So I'm going to go ahead and now do a break. So the break will end this case and jump out of the switch statement.
Yep.
Or you could control F like you did before. Also works.
If you don't do the break, it just letting you know, it will continue down into the other cases and execute those as well.
Yeah.
Which is sometimes useful because sometimes you have multiple states where you do essentially the same thing over and over again, but you still want to count the states. So you can just have the cases for all those states point to the same bit and then just break at the end of all.
Yeah. But in this case, no pun intended, we're just going to break out because we don't want to go through all the other cases yet. So let's go back to our state diagram here. And so our first state is turn on the LED. The next state is read the photo transistor. Now this one is kind of a longer string of it's a bit more instructions. And again, apologies, I do not have all this memorized off the top of my head. So I am roughly going to try to kind of copy this in here.
Explain you what it does.
No.
So,
It's also 8 or 7 if anybody has to.
So-
I don't know if you're planning to say the whole.
First thing it does is it starts the ADC, so it tells the ADC start checking what the voltage on it is. Second one is poll for conversion, so it waits for the conversion to finish because it takes the ADC some time to
These guys
settle
don't have to,
because
but
it's
that's why
reading.
they
So it'll wait for it to settle, at which point it'll generate an interrupt and it'll grab the ADC value from the ADC. And then yeah, he's just assigning the ADC to that.
Yes. Yeah,
And then he's stopping the ADC after that.
that is correct. So, yeah, so kind of just, reiterating what Leo said. The first one, that ret value, again, is just the type def. It's just a variable that will check if it's running okay. So if it started, it'll say HAL okay, essentially.
Yeah.
If not, it'll give an error. And then this will kind of check for the error as well. And then
that way. Usually we say if we make it an if statement. So if
right.
equals HAL okay, because that way you can put or not equals HAL okay, then you put the error handler in there.
Yeah.
But we're not doing any error handling here, so
Yeah.
just saying that that's also a possibility.
Yeah, and I kind of had that up there as well with the if statement and checking if it's not HAL okay, then run some system.
I mean, it's one option so that just in case it fails, you don't automatically just crash the system.
Right.
You can say, okay, I didn't get a value. Maybe just run it again or something like that.
Yeah,
There's
and
options.
in future things, I might recommend to do that. But for right now, this is
It's our
just
first major
this is less lines.
Yeah, saving the return value for debug purposes is perfectly valid.
Right. Yep. All right. So again, just saving the return value. And then next, we have the photo transistor LED on. This will be equal to the ADC value that we're going to be getting. So we're going to be reading the voltage coming off of in between the photo transistor and the resistor. So the division between those two, we're going to be reading the voltage there. It's going to go through our analog to digital converter and then give us a number representing that voltage. Then we're going to stop the analog to digital converter. And then again, we're just going to set the previous state is equal to the current state. That way, when we jump back out of this don't forget the break. So
I'm wondering if you have to start and stop it every time. There are some cases where you can just start it and leave it running. It's possible.
Yeah, well, I'll look into that a little bit later. But
for this purpose, this is fine.
Right. So now, once the break happens, it's going to jump out and then go through our main loop again, right? And now, let's say we're going through here, and if state is not equal to previous state, then it'll go through this case switch statement again. But you can see in here, we just made them equal to each other. Previous state is equal to state. Thus, this is not true, and so it'll just completely completely skip this if statement. It won't run the switch case. So that is the purpose of logging the state in the previous state. That way, we can only jump into this switch case once the state has changed. And you'll remember down below, every 250 microseconds, this function will run, which will change the state. But this adds 1 to the state, but it doesn't add 1 to the previous state. Thus, once it comes back to this if statement, it now has state being 1 more than the previous state, which will jump into the switch case. So the next thing that we want to do is turn the LED off. Luckily, it's pretty much the same exact process as turning the LED on, so you can just simply copy that and put it there. But instead of set, we're going to have reset. So the only thing I changed right here is set to reset.
You can hover over it, see that's a 0.
Yeah. And the set is 1. And finally, the last thing that we want to do is read our value again and change the variable. So I'm just going to go ahead and post all that same thing here, except this time we're not reading the photo transistor with the LED on, but instead we're reading with the LED off. And we went and defined that at the top, if you remember.
So save it to the other variable.
Yes. Now, the very last thing that we want to do, if we go back to our state diagram right here, we have it. So we now turned on the LED, read the photo transistor, turned off the LED, read the photo transistor again. Now we need to subtract the photo transistor readings from when the LED is on versus off. So this is just going to be simple. It's just PT diff. If you remember at the top, we defined that variable as photo transistor difference is equal to PT LED on minus PT LED off. So, yeah, I believe that is it. Oh yeah, I forgot. Yeah. So, in addition to that, if for whatever reason it's not case 0, 1, 2, or 3, it's going to jump to the default, and we don't want to run any code in the default. We just want to break it out.
Yeah, make sure it gets out safely.
Exactly.
You could also put an error handler in there in case,
Yeah.
Again, future proofing.
Yeah. You could, again, you could put an error handler which will kind of stop the code safely if it gets to that point.
Yeah.
But for our purposes, we're just going to break it out right now.
Error handler could also just be a debug code. So it sets a debug with a particular value, so you can go back to that value and figure out where it was. That's another thing that you can do.
Interesting, yeah. All right, so I'm just going to look at the little squiggly lines right here and see, okay, this one ends right here at the switch case, and this one right here ends at the if statement. So if it doesn't, if this is not true, then it'll just skip all of that and then just go to here and then go start back and then just kind of loop indefinitely. All right, now I believe this is pretty much it. I'm going to go ahead and build. So I would recommend everyone go hit the little hammer symbol in the top left right now to build it. And if you have any warnings, if you have any errors, let us know.
Looks like someone got an error. I see a lot of red.
Sometimes the red pops up as a baseline, but it still runs the actual code.
No, red usually means error, which means something wasn't defined.
Even still, sometimes you'll get the
No, or
like you mean the red highlight?
Yeah, the
not
red
the red
highlight.
text. Gotcha.
yeah,
We can
the
go back
orange
to
is the
code.
warning. So
Yeah.
orange will be fine.
Yeah, because I'll get y'all get something wrong during build process, but it still works.
Something
Something weird about the stuff is as long as you
How
still
can I
get.
tell if it's still working?
I
I know I
Well,
probably
it's telling
got
you the
something wrong
thing
with
that's
the
wrong is
spec.
this description here. Is
Yeah, in the terminal.
I'm not sure what. I think. Oh, it has to be.
So that red.
So
So-
oh, it's just capitals.
Huh?
Yeah.
Oh, just handle.
Error.
Yeah, that way. So yeah, usually if it's because it's a value that's defined in HAL, it'll usually highlight a
12.
different color when it's correct.
Expected and
Gotcha.
expression.
So you can rebuild that. That should be correct.
Switch.
Yeah, unfortunately the squiggly lines don't update until you build. Yeah, there you go.
I believe,
No problem.
Right.
I believe that needs to be a squiggly. Right, for the switch state. You don't mind going to the switch state.
Did you lose the console? Oh, it's just hidden, I think.
And
But that's how you would debug. You would be in columns, and then you would see all the there's the switch state.
Oh, sorry.
no, that's okay.
Um,
Was it just that? The
yeah,
third
that-
thing?
There you go.
Yeah.
Scroll up, go to this window and scroll up.
Yeah,
It'll
so
tell
all
you
it
what
is
the
just
error
this
is.
becomes
It should be this line. Conflicting types for state.
at the bottom. You would add.
oh, is this state?
Why is your code so clean? Oh my god.
You just add more gaps. And that's all it is.
Okay, for unsigned.
It also just looks nicer when you have the
Definition of state.
it running in that section, which is the green for the
Yeah.
like certain variables and stuff. Mine's blue. It's kind of ugly.
Oh
but-
yeah, go back
What
to the
else?
previous
There are
one.
more.
There's a
Oh.
bunch more, yeah.
I know. I don't have any backup.
No, you're good. I think you did fine, other than
Here, mine's just
Like when I first initialized it?
yeah, it's all
This
good.
spelled wrong.
It
Yeah.
popped up if I had errors, right?
Yeah, it would have
That's
popped out.
Yeah.
It's gonna be probably.
I think you should be good then.
first.
I am going
I know I
to-
made this squiggly mistake another time because I looked at it and it didn't look.
Oh, it'll be here actually.
It has some little squiggly.
It's telling
Yeah,
you
it'll
that
be there.
one of the places where you're performing an operation on it, you
And
accidentally
then
put U in 16T in front of it, which C is going to take as you were trying to initialize it again.
Yeah, you just
So
close them
it's
off
one of
then.
the, let's see. This
Yeah, see?
supposed to be
That's
that
it.
way.
That should be it. So you did fine, all things considered. Okay, so there's those. Identifier, GPIO pin.
I don't need all this change.
Oh, she already fixed those. Okay. Those were. You could try building again.
No, it's still there. Which line is it said?
GPIO pin needs to
Should
be
be
capital.
It's line. Looks like line 585.
Okay, that's that.
That same one.
This one as well.
So.
It wouldn't
Is there?
be
Oh, this
And
was.
then
right?
this one, variable state.
So you need to put it in the function. So this is what
Line
this was talking about.
5999.
Oh,
So-
because you have a you have a
Same-
semicolon here, so it's reading this as a
Tiny
function prototype.
Yeah.
You need to backspace that semicolon, so get rid of that semicolon.
Sure.
Open curly braces.
Fine, so we're done.
Void,
Uh,
period.
and then underneath that, closing curly braces.
So
Yeah,
now,
that's fine.
yeah,
And
that's
this one.
that should be kind of the syntax for if you have a function.
Yeah.
That the curly braces are what happens inside the function.
Yeah.
So the function right here, you're just defining it as a void, which just doesn't have.
Well, if you just put a semicolon after, what it is the function prototype, which is to say that it's a way of declaring that this function exists, but not defining it, which is useful because you technically have to define a function before it can be called, but sometimes you want the function for formatting purposes to be at the bottom of a piece of code, or in a totally different file.
I might give some supplemental stuff on just functions in general.
Yeah, no, C functions, especially when you're talking about multi-file
yeah.
systems, is quite involved.
Yeah, because
Global
functions.
storage.
Yeah, C functions are.
Yeah, especially when you talk about function pointers and whatnot. You shouldn't be using them, but they're there.
Still
Yeah.
building.
But anyway,
Is
yeah,
there any
you
other
just,
place you
you just
define
need to
state?
actually define the function that needs
Okay, there you got state, vertical state. Oh,
Yeah, it
no,
works.
never mind. We did fine.
Yeah.
No more
Okay,
problems.
cool.
That was it. You did well, other than the
Alright.
squiggly for when you're doing functions. As always, it's parentheses for like what you're gonna do with the void function, and then it's
Alright.
squiggly for when you're doing like an actual.
So I'm gonna run the debug. Oh,
And other
I
than that,
cannot run the
syntax
debugger
and
if I'm
you're
not
fine.
plugged in.
Just be okay.
And then we should be able to flash our code, so we'll be fine.
All right.
Or debug. It just depends on how Adam wants to run.
Well, I mean, you're gonna flash it either way, but
Yeah.
debug just runs it interactively.
Mm-hmm.
All right. So,
It's in debug mode.
I am in debug mode. So right now, nothing is running because it's waiting for me to either start or step through.
Yeah.
In this case, I'm just going to go ahead and click the resume, which will just start the code.
Yeah, we can't actually see the live expression
Oh.
of the values because it's all the way off to the right. I think the screen is cutting it off. There you go.
Well, nothing is happening.
Well, the encoder counter.
What's happening? Let me pause. Where am I? PT. Let me just make sure these are the same.
I mean, it would
Oh,
have failed to initialize if
yeah.
just make sure are you actually running the right variables.
The variables. Yeah. This is from the other.
Why is that USB? Oh no, that's fine.
Yeah. I'm gonna delete this one. I'm gonna delete. I'm just gonna remove them all and add them back because that was from my last one. I don't know if for whatever reason. I'm just gonna start off with just PT diff. So that is the main one that we want to be.
0.
Well, I haven't started it yet.
It's still 0.
It is still 0. All right. This is, whoops, I didn't mean to completely terminate it. This is the beauty of STM32s because we can do something called step through debugging. Step through debugging is, I'm actually glad this didn't work.
Yeah.
I'm glad this
You
didn't
can
work.
show the debugging process, which you will all be very familiar with if you work with this platform.
Yes. So the beautiful thing about STM32s is you can actually step through each code. Each line by line. And yeah, you can use breakpoints as well. But I don't know if you guys have used MATLAB to do that. I know oftentimes you could do like step by step in MATLAB as well. But in this case, I want to just go ahead and step by step and see where my thing went wrong. So this is just doing the initialization stuff.
Just stepping over all the function calls.
Yeah.
You can step into the functions as well, but you don't need to check that.
Yeah.
I'm just saying it's an option.
Yeah. All right. So now now we're in while one. So first it's gonna check if I'm gonna go ahead and add the other
You should at least add state because we need to monitor that state variable.
So right now it's state and
I have a funny feeling your interrupt's not calling, not going.
I'm thinking that too. So right now, I'm at this line. And right now it's just checking the if statement. If state is greater than 3, make it equal to 0. In our case, state is equal to 0. So this will be false, so it won't do anything there. Now it's going to check if the state is not equal to previous state. And I'm just going to add previous state here just so we can see what's happening. Right now it's 1 because I'm starting them to be different.
Oh, okay.
We want to start right away in this case, so I'm just having be different.
Okay,
Next, it's going to jump into our switch statement or switch case, and it's going to go into case 1.
No, your state is 0 right now. Your
Yes.
previous state is 1 because
Sorry, case 0. Sorry, I said
case
1. I said 1. I meant yeah. I know. I should fix that. I should make them either 0, 1, 2, and 3. All right, so it should turn that pin on right now. Set the previous state to equal to state. So we should now see that change to be 0, which is correct. And now it breaks. It just runs that little bit, goes back to here. And
it's basically going to get stuck there because it looks like the interrupt's not calling at all. You would see the interrupt call at this point.
Yeah.
One thing you could do, Adam, go down to the interrupt handler
and do a breakpoint.
Breakpoint
I'll put a breakpoint there.
Yeah, that way if you run it, you'll see if it's calling it or not. You can you see that blue bar on the right?
Yeah, I could just double.
Yeah, that's your best bet.
All right, so now I have a breakpoint right there. So I'm gonna go back to my live expressions and just hit resume, and I'm gonna see if
It ever enters, which it's not.
it's not. If it ever entered right there, it would stop my code right there. So for an example, I'm gonna go ahead and double click that, go up to here, and do a breakpoint.
At the end of like the loop.
Yeah, at the end of the loop. So I'm gonna do a breakpoint right there.
Actually, that's not gonna work. You're outside the function.
No, yeah, it should work. No, the end of the function's right there.
Oh, okay, yeah.
Yeah.
Okay, you're good.
If I hit resume, boom, it just hit right here and stopped.
Yeah.
So I know that our code is never going to interrupt. I got to figure out why.
Yeah. Did you start the interrupt?
Did we initialize our timers?
Yeah, I mean, it looks like it started. Yeah.
Let me compare to the one that does work.
Oh, the master code.
This is the only difference.
Maybe try copying that in instead.
Yeah.
And seeing what happens when it's called, because it looks like it's trying. It could be that it's trying to start and it's not.
It's not starting. All right, so I'm gonna go ahead, terminate it.
I think there's a restart.
I'm sure there is. I'll check it out next time.
Well, you need to rebuild it anyways.
Yeah. So I rebuilded it. And then we go into the debugger again.
Just make sure you did configure all the clocks right.
I did.
Okay.
I'm just gonna waiting for the debugger to connect.
Yeah.
And all right, I'm just gonna go ahead and resume. Look at our live
It
expressions.
looks like it did definitely random.
Oh, it went to the breakpoint.
Okay. Set the breakpoint back on the interrupt.
I will.
See it. It looks like it's still not calling.
It doesn't look like it is. Yeah.
Yeah, it's definitely not calling.
It's not calling, yeah. So let me. Whoops. All right, back here. Let me figure out what's happening.
Yeah, at least we know what's wrong.
Yes. So that's the beauty of Cube IDE and STM32.
And also the horror.
Yeah, and also the horror. But in Arduino or something else like that, there is no step through debugging and there is no breakpoints.
Yeah,
So if I am like, hey, nothing is happening, I have no idea why until I manually go through the code, click through it. You have to you have to go through and add print statements to see if it ever gets those print statements, but you can't actually stop the code once it gets there. And it becomes very, very annoying to debug. So it can take a very long time to figure out what is actually wrong with your code. In this case, it was very easy. That being said, we now have to figure out what happened. So the timer should have started. It didn't give an air handler at the beginning. Meaning the next thing I want to check is.
I mean, there's another chance that somehow state isn't updating. Or the problem is you have multiple projects open. I'm wondering if you're actually running the right.
Let me close others. All right. You know what? This is also another thing. I don't know what this.
Two views.
I do have two views, and they are of
I think it's
the same exact file.
Different parts of the same
I don't know how to. I don't know how to get rid of it.
I don't think that's going to affect your code execution.
I don't think it'll affect my code either. So I've just been
Window maybe. At the top.
window. Oh.
And then appearance
Editor, I think.
or editor. One of those two.
Should be able to.
Toggle split editor.
Yeah, toggle split editor.
Oh. Well, now it's a different problem. But we unclick the file.
All right, it's the same file. It should be good.
Head out right now.
All right, that's fine. You know, how about we check it on one of your computers? Let's see if you guys did it good.
Oh.
Does anyone have a USB input?
Okay.
Oh, wait.
What did I
Insomniacs
enable
after
the
school.
NVIC
That is.
on the internet?
I did.
Insomniacs
After school. That show gave me like.
Yeah, I enabled it.
Yes, the global NVIC.
No, it's not at all. Well, I mean, I guess so,
You're
because
still
it has like
debug
drama
mode.
stuff,
Yeah,
but
Mm.
it's a short show.
Mm-hmm.
It's very realistic, and the characters aren't crazy over the top like personalities, or they're not like super stacked with like they're just over the top high school.
Mm-hmm.
They're very regular looking, and
Yeah.
their problems are like that. Basically, these two. students,
Oh.
like
I don't think I did actually.
Yeah,
they
there
find
it
that
is.
they can
That will do
rest
it.
in-
Yeah.
If you don't enable the NVIC,
And so
Um,
while they're doing
it's
that,
like
they get
the-
caught by
it's
the
like the
teacher, and the
whole,
teacher says, okay, well, you guys can
interrupt
still
table.
have
If you
this,
It's just-
but you need to
if you
start
don't
the
enable the
astronomy
interrupt,
club.
it won't actually.
And so it's
roll.
about
that's exactly what it is. I skipped over that step in
They try to get more people interested.
and yeah. So they go over it in this. I absolutely skipped it.
Yeah, it's right there. You just walk past it. It's that you just have to click the.
I would highly recommend.
I did this actually.
I mean, yeah, if you did that, because that is the NVIC. I mean, it's just in a different window.
I did do that.
Can we just go and make sure? It should be.
Let me RCC. This is
Yeah, if you click
Master.
That, it should be.
I did-
believe It was generally
yeah. You're good.
really good presentation.
I
I'll see you next week.
see him.
Yeah, just pull it out to the right so we can see the checkbox.
See if I can. See if I
Because
can.
that's later.
So
Go scroll down
this
on
is the NVIC set. Wait, what?
that. Yeah, you didn't have it enabled.
I thought I clicked that.
Well, that solves the problem.
All right, cool.
I saw you do it.
Yeah, I could have sworn I clicked that.
It's possible you didn't save it somehow.
That's weird.
Well, that's why we checked.
Yeah. So that's the process of debugging.
I wonder if you had the wrong IFC open. Anyway,
I could've.
Regardless, we found it now.
All right. So now,
It should work now.
I'm.
You're disconnected.
I am.
This is more interesting. God damn it, Leo. Screw it.
All right. I'm about. Yeah. I know I'm going a little bit over time, but
We just want to see this work, Adam. Go do it.
yeah, I know.
We want you to prove that you know what you're doing.
I just missed that. All right. So
I think I'll be the judge of that.
okay.
You can't see the variables again.
That's all right.
I can be the judge of that.
Hey.
I
So
never
okay.
I was
Oh.
the only judge.
So it hit that breakpoint and stopped. So now we know it goes into this. So it just went into here, hit the breakpoint, and stopped. So I'm going to go ahead and resume it now. Okay, there's still a breakpoint there. Whoops. Now we have our distance sensor.
Yeah, you see P-diff is changed.
Yes. So our state and previous state are changing extremely fast. And I'm going to go ahead and do just PT LED on, just so you can see it. And then I'm also going to do PT LED off. So we're reading a value of around 30 in the ambient room, and right now 100. But as I move my hand closer, you can see that value increasing and decreasing. So we can get it close to 2,000 if we get really close. So we can use this to measure our distance of the walls, but now we're not just measuring it every single second and having all of our infrared on at the same exact time. We're running through a state machine right here that is turning on the LED, waiting for the receiving signal to be at its peak, sampling that, and then turning off the LED, and then waiting for our received value to be at its valley, and then subtracting those two and getting a result. So this is a much more efficient way to do what we did last week with the analog to digital converters. And I'm going to assign half homework, but if you guys can repeat this with, let's say, 3 of them. So next week, I'm going to have 3 of them in a row. And if you guys come in with the same exact code, but just repeated 3 times instead. So now instead of 4 states, we might have 12 states, or 0 through 11 if you're going to count it like that. You can also do, I see Leo sitting there thinking that, so you can also have a function that changes each one of those values inside of them. that is the more efficient way to do it.
I would say my way to do it would be encase that entire state statement, that switch case statement in a function, and then make one of the parameters for that function
The value for the pins and stuff.
Yeah, the value for the pins, and then basically create multiple versions of that, so you're calling it for an individual pin.
Yeah, that is.
You will probably have more state.
Yeah, there's going to be, that's a little bit more involved. If you do it at all, that's great. But that involves going back to the IDE, choosing more of those pins to be analog inputs and GPIO outputs, and then having that, and then adding that to the states. So, and then you also need to add how many states there are and everything else like that. There are more efficient ways to do it. I saw Leo rolling his eyes when I said that. But for right now, if you guys can at least do that, then, I'd call that a success.
Yeah.
All right. So that's pretty much it. If you guys want to test this out yourself, I can pass this around.